let's compute T4. Sorry, we've computed T4. Let's compute T2 of n. So what was T2 of n? T2 of n was equal to 2 plus the sum from I equals 1 to n of 3 plus the sum from j equals I to n of 6. Okay, so we have a 2, and then we have a sum of two things added together. So let's just apply the addition rule and see where it goes. You might have noticed there's something weird in here. Okay, there are two sums that are somehow linked. Okay, we'll get to that. But let's first apply the addition rule. So this is 2 plus, now we are getting used to this. So this is the sum from I equals 1 to n of 3 plus, okay, the sum from I equals 1 to n of whatever this is. So this plus the sum from I equals 1 to n of the sum from j equals I to n of 6. So I've just blindly applied the addition rule. Okay, and let's continue. This is equal to 2 plus, we can pull out the 3, and then we get the sum from I equals 1 to n of 1, which is 3 times n, plus, okay, now we have something interesting. Well, we'll just keep it here. Sum from I equals 1 to n, sum from j equals I to n of 6. Okay, so, you're looking at this and saying, wait a minute, this is the product of sums. We know how to compute sums. What is a product of sums? We never talked about a product of sums. Well, this is not actually a product of sums. This is what we call nested sums. Just like you can have nested loops, one for loop inside another for loop, you can have nested sums, one sum inside another sum. Okay, and there's nothing wrong with that. It means that I'm computing, it's not that I'm computing a sum times a sum, it's I'm computing a sum of a sum. Okay? So you can think of this as the function f of I. Okay, so in order to compute nested sums, I'm just going to state it as a rule, the nesting rule. Okay, so the nesting rule. Okay. So what you do is when you have nested sums, or a sum inside another sum, start with the innermost sum. Okay, and compute it as a formula. So it's almost like you do a it's almost like you have to do two sums. You as a separate exercise, you have to look at this innermost sum and compute it as a formula. Okay, and then replace the innermost sum with the formula. Okay, so replace the innermost sum with the formula, and then continue to work outwards from the innermost sum to the outermost sum. So work outwards, work your way out. So if you still have nested sums, then you do the innermost sum again, replace it with a formula, and again, and again, and again, and until you get to the outermost sum, at which point you just have that sum to do, and you're done. So let's see how that works here. So this is, okay, so we have to compute this innermost sum. This is the nesting rule. So almost as a separate exercise, we have to compute the sum from j equals I to n of 6. Okay, and now we notice something else. All the sums we had before, the lower limit, j starts at a number like 0 or 1. Okay, here we're starting at I. Nothing wrong with that. It just means that we have to try j equals I, see what the function is, add it to j equals I plus 1, j equals I plus 2, all the way up to j equals n. There's nothing wrong with that. Okay. Now, to compute this, we can apply the constant rule. So this is 6 times the sum from j equals I to n of 1. And the sum from j equals I to n of 1, this is a common sum. This is 6 n minus n minus I plus 1. So you're going from I to n and you're adding 1. So it's just the number of terms in this sum is n minus I plus 1. So we can put it in here. 2 plus 3n plus the sum from I equals 1 to n of 6 n, okay, minus 6I plus 6. Okay, wasn't so hard. Start from the innermost sum, compute it as a formula, replace the innermost sum, and work your way out. Okay, and now back to the addition rule. This is a sum of terms added together. So this is, and now we have constants, so we can pull out those constants. So this is twice 2 plus 3n plus the addition of individual sums. So this sum is 6. The sum from I equals 1 to n of 6 times n. But n is also independent of I. So this whole thing is a constant. So plus 6n times the sum from I equals 1 to n of 1. Okay, now, slight tweak to the addition rule. What if you have a term that's subtracted? No problem. You just subtract the sum, because subtracting a term is just adding minus of the term. So we have minus, okay, we pull out the 6 times the sum from I equals 1 to n of I, plus 6 times the sum from I equals 1 to n of 1. Okay. So this was the addition plus constant rule. So you see, those two basic rules are all I'm using together with common sums. Okay? And where do we go from here? Well, this we know is by a common sum is 2 plus 3n plus 6n times n. This is a common sum. So n times n is n squared. Minus 6. This is a common sum. Sum of the first n integers times 1/2 n plus 1 plus 6n. Okay? And this is equal to 2 plus 3n plus 6n squared minus 3n squared minus 3n plus 6n. Okay. And that, if we want it to be done, is a formula. It doesn't involve a summation, but it's an ugly formula because it's not simplified. So let's simplify it. This is just 2 plus 3n, minus 3n plus 6n. So plus 6n squared minus 3n squared, so plus 3n squared. Boom. We have computed T2 of n. Fantastic. Let's do one more harder example. Another example of nesting. So let us compute the sum from I equals 1 to n of the sum from j equals 1 to I of I times j. Okay, so it's an example of a nested sum again. So we're going to have to apply the nesting rule. Okay, and the nesting rule says as a separate exercise, compute the innermost sum. So we need to compute the sum from j equals 1 to I of I times j. And then you look at this and you say, but wait a minute, this upper limit is the index of the outermost sum. Is that allowed? No problem. This just says the values of j range from 1 to I, and you have to add up this term as j ranges from 1 to I. There's no problem there. Okay. And let's see if we can just compute this sum using our rules. So this is equal to, well, I is a constant because it does not depend on the summation index j. So we pull I out, the sum from j equals 1 to I of j. This is a common sum. It's the sum of the first I integers. So this is I times 1/2 I plus 1, which is 1/2 I cubed plus 1/2 I squared. Okay, so we've computed this innermost sum. We have to replace it. So we replace this guy with 1/2 I cubed plus 1/2 I squared. So we have the sum from I equals 1 to n of 1/2 I cubed plus 1/2 I squared. It's ideal for the application of the addition rule. Okay, but also we see these constants are half, which we can pull out. So this is equal to 1/2 sum from I equals 1 to n of I cubed plus 1/2 the sum from I equals 1 to n of I squared, which is equal to 1/2. Now this is a common sum. 1/4 n squared n plus 1 squared plus 1/2 the sum of the squares. This is the sum of the cubes, the sum of the squares. It's a common sum. Okay, so 1/2 n plus 1, 2n plus 1. Okay, and then when all is said and done, I have 1/8 n squared n plus 1 squared plus 1. Oh, sorry, there's a 1/2 here, and I have to do an n over 6 to make this. The sum of the squares is n over 6 times n plus 1 to n plus 1. So then I have n plus 1/12 n plus 1 to n plus 1. Okay, that's a formula. Looks pretty decent, but if we wanted to simplify it into something of this form, we could. It's just algebra. So what we would end up with is 1/12 n plus 3/8 n squared plus 5/12 n cubed plus 1/8 n fourth. Okay. Whew! This complex sum. We did all the hard work, and we get a, formula. We can't look at this formula and say, oh yes, I was expecting that, because I don't know anyone who, when looking at this complex sum, is expecting that formula. Okay. But the point is we can do these complex sums. It's a lot of work, okay, and it's hard work, but if you want to evaluate a running time exactly, or you want to compute a sum exactly, well, you have to compute these sums. Okay. But now, we might say, do we really have to do all this summation and stuff, when we want to analyze a running time? Well, typically, when you want to analyze a running time, you first get it into the form of a sum. And now, okay, we want to then capture the essence of the algorithm by understanding how that sum behaves for large inputs. Okay? And to capture the essence of an algorithm, we don't necessarily need the exact value of the sum. Maybe an approximate, an estimate of the sum is good enough. Because A, we're only interested in when n gets large. Okay? And that turns out to be the case. In order to capture the essence of an algorithm, we really just need the growth rate of the sum, how it grows with n. Okay? And that leads us to asymptotic analysis. So let's erase and let's come back and discuss asymptotic analysis. Okay, let's do a speed erase. Bam, 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 bam. Okay, practice. Okay, compute the sum from I equals 1 to 3, the sum from j equals 1 to 3 of 1. So this is practice number 1. Compute the sum from I equals 1 to 3, the sum from j equals 1 to I of 1, okay, and 3. Compute the sum from I equals 1 to n, and the sum from j equals 1 to I of 1. Okay. So pause the video, give you a couple of seconds to pause. Okay. Now, let me tell you the answer. If you pause the video and got all of these, then you're beginning to get nested sums. And if you're just here for the ride, okay, if you got this equals 9, this equals 6, this equals 1/2 n plus 1, you are on the money when it comes to nested sums. Okay. And if you didn't get these, well, please read the text and work these examples out. It would be very beneficial.